Let's look at double integrals in polar coordinates. Just try to evaluate the integral from 0 to 4, 0 to square root 16 minus x squared of 25 minus x squared minus y squared dy dx. We can't perform the first integration because in order to do so, because this is all under the square root, we'd have to have a y on the outside, really a negative 2y on the outside, and it's just not there. And reversing the order of integration will not help. We can't integrate this with respect to x either. Polar coordinates can help us out. Recall that the polar coordinates of a point are r theta, where r is the distance from the point to the origin, and theta is the angle between the line segment from the origin to the point and the positive x-axis. So the polar coordinates of this point would be r theta, where r is this distance and theta is this angle. For example, find the polar coordinates of the point with rectangular coordinates 3, 3. R in this case, okay, so here's the point 3, 3. R is this distance, which is 3 root 2 by the Pythagorean theorem, and theta is this angle. It's 45 degrees, in other words, pi over 4. We always use radians with polar coordinates. So the polar coordinates are r theta, 3 root 2, pi over 4. Okay, let's evaluate the integral from 0 to 4, 0 to square root 16 minus x squared, square root of 25 minus x squared minus y squared dy dx by switching to polar coordinates. Dy dx is r dr d theta. Why? Where does the r come from? Well, it's like substitution. In Calculus 1, if u equals x squared, then du equals 2x dx. We don't really ask where the x comes from. It's just that du is 2x dx. So in the same way, dy dx gets replaced by r dr d theta. And the integral of f dy dx is thus integral of f r dr d theta. So now we change the integrand, the function we're integrating. Okay, the square root of 25 minus x squared minus y squared, really that's the stuff under the square root sign, is 25 minus x squared plus y squared. In other words, 25 minus r squared. So this integral is really the integral of 25 minus r squared, r dr d theta. Multiplying the r's together, we get 25r minus r cubed dr d theta. Now let's find the new limits of integration. What region in the xy plane are we integrating over? Okay, y goes from 0 to square root of 16 minus x squared, and x goes from 0 to 4. So this is the region we're integrating over. This looks like a quarter of a circle, because it is. Y equals square root of 16 minus x squared is y squared equals 16 minus x squared. In other words, it's x squared plus y squared equals 16, which is a circle of radius 4 centered at the origin. This is the entire circle. This is just the upper half of the circle. We get only the upper right quarter because y goes from 0 to square root of 16 minus x squared, and x goes from 0 to 4. So we don't get the whole circle. We don't even get half a circle. We just get that. Thus, r goes from 0 to 4, and theta goes from 0 to pi over 2. So those are our new limits of integration. The double integral of 25r minus r cubed dr d theta. Let's insert those limits of integration. 0 to pi over 2, 0 to 4. Integrate with respect to r, and we get 25r squared over 2 minus r to the fourth over 4, as r goes from 0 to 4. Plug in 4, that's what we end up with. Simplifies to 400 over 2 minus 256 over 4, 200 minus 64. In other words, it's the integral from 0 to pi over 2 of 136. Integrate that, we get 136 pi over 2, in other words, 78 pi. So that's the integral. Okay, let's evaluate this integral. Negative 5 to 5, 0 to square root 25 minus x squared y dy dx. It turns out that polar coordinates are going to be helpful here too. But that raises the question, how do we know when we should switch to polar coordinates? Well, the region in the here's some hints that we should. The region in the xy plane we're integrating over is a circle or part of a circle. Turns out that that's what we have here, but it's not obvious. You'll see later why that's the case. Or the integrand has x squared plus y squared under a square root sign, like square root of x squared plus y squared, or square root of 9 minus x squared minus y squared, or as we saw in the previous problem, 25 minus x squared minus y squared, all under the square root sign. Okay, so y dy dx is r sine theta times r dr d theta, because dy dx is r dr d theta, and recall that x equals r cosine theta, y equals r sine theta, and x squared plus y squared is r squared. That's how we convert from rectangular to polar coordinates. So multiply the r's together, and we get r squared sine theta dr d theta. Okay, y goes from 0 to square root of 25 minus x squared. X goes from negative 5 to 5. This looks like a circle, and it is. This is actually a semicircle. Y equals square root of 25 minus x squared. y squared equals 25 minus x squared, in other words, which is x squared plus y squared equals 25. So this is a circle of radius 5 centered at the origin. This is just the upper half of the circle, that semicircle that we saw. Okay, so in this case, if we have a circle of radius 5 centered at the origin, it looks like r is going to go from 0 to 5, and theta goes from 0 to pi. So again, r goes from 0 to 5, theta goes from 0 to pi, and we have r squared sine theta dr d theta. Integrate with respect to r, we get r cubed sine theta over 3 from 0 to 5. Plug in 5 and 0, and we get 125 over 3 sine theta d theta. Integrate that with respect to theta, and we get negative 125 over 3 cosine theta from 0 to pi. So 125 thirds times negative 1 minus negative 125 thirds times 1. That all works out to be 250 over 3. Okay, how about these? Let's find the volume of the solid between the surfaces z equals 8 minus x squared minus y squared and z equals x squared plus y squared. Okay, so here we've got the elliptic paraboloids and the volume of the solid below the surface. So this is the 8 minus x squared minus y squared. And this bottom one is x squared plus y squared, z equals in other words. Okay, the volume of the solid below the surface, z equals 8 minus x squared minus y squared. And above the surface, z equals x squared plus y squared will be this integral. Okay, because this is the stuff on top, that's the stuff on the bottom. So it's 8 minus x, 2x squared minus 2y squared divided by dx. What region in the xy plane are we integrating over? Well, that's just the intersection of these two surfaces, which looks like it ought to be a circle, and it is. Because the intersection of the surfaces z equals 8 minus x squared minus y squared and z equals x squared plus y squared, if you're looking for where they intersect, just solve it as a system of equations. They're both equal to z, so they're equal to each other. 8 minus x squared minus y squared equals x squared plus y squared. That is, in other words, 2x squared plus 2y squared equals 8, which is x squared plus y squared equals 4. This is a circle of radius 2 centered at the origin. So that, my friend, is the region that we're integrating over. So in this case, r will go from 0 to 2, theta goes from 0 to 2 pi. Okay, so again, we had 8 minus 2 times x squared plus y squared, which is 8 minus 2r squared, r d theta, 8r minus 2r cubed dr d theta, and as I said a moment ago, r goes from 0 to 2, theta goes from 0 to 2 pi. Integrate with respect to r, we get 4r squared minus r the fourth over 2. Plug in 2 and 0, we get 16 minus 16 halves, which is 8. Integrate 8 d theta from 0 to 2 pi, and you end up with 16 pi.